Change of plans. I want to go back to solving triangles because we only did half of the solving triangles business. And then we started with the usual solving right triangles. So, set your way back machine to the beginning of the semester when we were solving right triangles. Let's recall the tools that we had for solving right triangles. We had the sum of the angles is 180 degrees. In a right triangle, we had the Pythagorean theorem. The sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. And we had our trigonometric ratios. So we had those three things for our tools. Sum of the angles, so that would mean alpha plus beta plus 90 is 180. This is true for all triangles, which means it's also true for right triangles. Alpha plus beta plus 90 is 180. We had the Pythagorean theorem, where a squared plus b squared equals c squared. And we had our trig ratios. Sine theta is opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. And tangent theta is opposite over adjacent. Those are the three tools that we use for solving triangles. The trig ratios we use not only for finding one of the sides, but we use inverse trig functions for finding the angles. So we also were able to rewrite our trig ratios to solve for angles. So we could say that theta is sine inverse of opposite over hypotenuse, or cosine inverse of adjacent over hypotenuse, or tangent inverse of opposite over adjacent. We've since seen some things that we know changes our view of how these inverse trig functions work. We know that when we we use the inverse trig function, that's going to give us a reference angle that we have to place into quadrants. We're not worried about that here because we're trying to solve a right triangle. And the angles that we're going to be looking for, alpha or beta, are going to be acute angles anyway. They're going to be sitting in the first quadrant. So all we need is the reference angle. So we don't have to worry about that doing the quadrant business because we're not solving an equation. We're solving for an angle that we know is going to fit in a right triangle. So we know it's going to be an acute angle. All we want to do now is take out the solving right triangles part. Let's take the right out of the solving right triangles parts and solve non-right triangles, solve oblique triangles. And we still have a bunch of tools. So here's our new thing. We want to solve oblique triangles. We want to circle back to solving triangles. This is one of our important things that we do in trigonometry. Get some information, triangulate, figure out the rest of it. Oblique just means non-right triangles. So oblique triangles means that we're not given a right angle. We're still playing the same game. I've got to give you 3 pieces of information. In this version of the game, you're not given that one of the angles is a right angle. The solving triangles game is still given 3, find 3. Solving triangles game is given 3, find 3. Solving right triangles means one of the pieces of given information is that one of the angles is a right angle. Now we're just taking that part out. This means we're going to have to develop a new set of tools for solving our triangles. Since we have a non-right triangle, I'm going to try to draw it where I don't draw gamma as a right angle. Every time I try to draw a non-right triangle, I end up with the right angle at the top. It just looks like a right angle at the top. I don't know why I can't draw oblique triangles, all right triangles. I don't know what the problem is. But in this case, we don't have a right angle, which means we don't have a hypotenuse. No right angle and no hypotenuse means that our Pythagorean theorem is out. Our trig ratios are out. Even though tangent has opposite and adjacent, that's opposite and adjacent where the third one is the hypotenuse. So no right triangle and no hypotenuse means we don't have the Pythagorean theorem, and we don't get to use our trig ratios in the same way. No right angle means no hypotenuse, means we're not allowed to use the Pythagorean theorem, means we're not allowed to use the trig ratios. We're going to have to find replacement tools for those 2 things. And this no trig ratios, I mean, sine and cosine is obvious because they have hypotenuse right in there and we don't have a hypotenuse, but this is even for tangent. Even though tangent doesn't say hypotenuse, we can't look at the 2 sides and say, well, which one is adjacent? Right? Opposite is fine. If you have an angle, there's just one side opposite, but now these 2 sides, one of them is not a hypotenuse. So which one is the adjacent? The answer is neither one of them. So we need replacement tools for our Pythagorean theorem, and we need a replacement for our trig ratios. One of our tools still works. The sum of the angles, still 180. Good old angles, we can always count on you. So I still get to say that alpha plus beta plus gamma is 180. Some of the angles, that one's still in play. We need a replacement for a Pythagorean theorem. Here's our replacement for the Pythagorean theorem. It's called the Law of Cosines. We're going to write down the law of cosines. It's going to start off real suspicious. Here's the law of cosines. It says c squared equals a squared plus b squared. Now I know you're thinking, dude, isn't that just a Pythagorean theorem? I'm going, no, because that c is not a hypotenuse, it's just an angle, and I'm not done writing. I just want to pause and point out that the law of cosines starts off by looking like the Pythagorean theorem, but there's some extra to it. It's like in Raiders of the Lost Ark, you know, there's some more stuff on the other side. On one side, it's just a Pythagorean theorem. And it's like, oh, dang, what if there aren't any right angles? You know, because it was just burned into the dude's hand. But on the other side, that's where the other term shows up. And it looks like this, minus 2ab times the cosine of gamma. That's the law of cosines term. That's the extra. Law of cosines looks like the Pythagorean theorem with that extra term, minus 2ab cosine gamma. So it's like I got c and has the cosine of gamma in this one. Now, I just pointed at this and said this one, because there's two other ones. So annoying. There's a c squared, and a b squared, and an a squared version of the law of cosines. So there's going to be three versions of the law of cosines, but they all follow the same pattern. Once you can see the pattern, it's all over. You just have to remember the pattern. This is the structure of that other term, minus 2ab cosine gamma. So let's write down the other two versions. The other two parts of the law of cosines, the second one starts off with a b squared, and it's a squared plus c squared with that other term, minus 2ac cosine beta. So it's like we're like rearranging the Pythagorean theorem, right? B squared equals a squared plus c squared minus 2ac, whatever we have here, times the cosine of beta, the angle opposite whatever we're squaring on the other side. But wait, there's more. There's also an a squared version, and it follows the same pattern. So we have a squared is b squared plus c squared minus 2bc cosine alpha. This is our replacement for the Pythagorean theorem. This is a generalization of the Pythagorean theorem. The Pythagorean theorem is the law of cosines that only works once. Notice that if I replace gamma, if I make gamma a right angle, then this term has a cosine of 90 degrees in it. Cosine of 90 degrees is equal to 0. So this is minus 2 times a times b times 0. This term drops out. If gamma is equal to 90, the law of cosines becomes the Pythagorean theorem. So the law of cosines is like super Pythagorean theorem. I don't know how this is not named after somebody. I don't know how Pythagoras is like, oh, this is my theorem. And people are like, oh, weak. Here's the law of cosines. And Pythagoras is like, oh, no. Imagine the whole anime fight in my head. Pythagoras comes up, it's like, I'll use the Pythagorean theorem. Ha 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 ha. And then the hero's like, oh, but this is not a right angle. And Pythagoras is like, oh, and he like explodes. And he's like, oh, And the observer's like, what's going on? It's over 90 degrees. It's, you know, Pythagorean theorem doesn't apply. So if gamma is equal to 90, the law of cosines is equal to the Pythagorean theorem. The law of cosines is the Pythagorean theorem, only better. If gamma equals 90, we get the Pythagorean theorem. Note that if beta is equal to 90, then b is the hypotenuse, and it's still the Pythagorean theorem. Hypotenuse is the sum of the squares of the other two legs. The reason that I start off with c squared equals a squared plus b squared minus 2ab cosine gamma is because then you only have to remember Pythagorean theorem with this extra term, minus 2ab cosine gamma. Just remember that extra piece. Then you just need to cycle through the different letters. Move the b squared out front. B squared is a squared plus c squared minus 2ac, always matchy in here. Cosine of beta, always the angle opposite. B and beta got this whole thing surrounded. Then you just need to cycle a squared and alpha to be on the outside. A squared is b squared plus c squared minus 2bc, always the same as these two. Cosine of alpha, opposite whatever's being squared on the other side. It's patterns. We want to recognize the patterns. We don't have to remember three things. We have to remember one thing, or just one pattern, and it's based on the Pythagorean theorem. You just have to remember minus 2ab cosine gamma, and then be able to translate it. How's that okay? There's also the trig ratios that have to get replaced. The trig ratios always have hypotenuse in them. And even tangent is out, even though it doesn't involve hypotenuse, it does say adjacent, and an angle has two adjacent sides. And I can't call one of them a hypotenuse, so I can't say tangent of theta is opposite over adjacent, because adjacent doesn't mean anything without a hypotenuse. So, part C. No hypotenuse. No trig ratios are allowed because there's no hypotenuse. So I got to replace that tool in our toolbox as well. Here is our replacement for our trig ratios. We're going to use the law of sines. We're first going to express the law of sines in its practical form. Then we're going to state what it means, how to read that form. And then we're just going to go say, okay, that's fine, that's fine. I'm trying to remember this practical form. Here's what the law of sines says. The ratio of the sine of an angle to the side opposite that angle is constant in any triangle. So that means that the sine of alpha over A is equal to the sine of beta over B is equal to the sine of gamma over C. That's the law of sines. This is how you would state that, state the law of sines in words. To use it, you're just going to write sine alpha over A equals sine beta over B equals sine gamma over C. And really, you're just going to pick the two that are most applicable to your current situation. But if someone says state the law of sines, then you'll say that the ratio of the sine of an angle to the side opposite that angle is constant in any triangle. Just like with the Pythagorean theorem. If someone says, what's the Pythagorean theorem? Most people would just say a squared plus b squared equals c squared. But if you want to state it in sentences without just writing a formula where we have to assume that the reader understands, or the person we're talking to understands, that c is the hypotenuse, you could say the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. I would state that in. Okay. It just seems like a lot to remember because it's a lot to remember, and you have to remember all of it all the time. Look for your patterns. If you need to write down the law of cosines, remember that it's a generalization of the Pythagorean theorem. And start off with c squared equals a squared plus b squared. And just remember the form of that term, minus 2ab cosine gamma. And then if you have to use one of the other ones, just switch things around. B squared equals a squared plus c squared minus 2ac cosine theta. A squared equals b squared plus c squared minus 2bc cosine alpha. It's the Pythagorean theorem plus. Well, minus, but you know, with an extra term. The law of sines is a lot easier to remember. Sine alpha over A equals sine beta over B equals sine gamma over C. Now, with all this extra stuff running, these are the tools that we need to solve oblique triangles. And with all this stuff running around, it seems like it would be difficult to deal with all this and decide what our strategy is going to be. Your general strategy will look like this. Can you use the law of sines? Because it's so simple. I really want to use the law of sines. If you can use the law of sines, use the law of sines. If you can't, use the law of cosines because you have to. That will happen at most. If you don't like to use the law of cosines, at most, you have to use it once as an opener. Our strategy from before, based on our first piece of information, the sum of the angles is 180 degrees. As soon as you have two angles, subtract to find the third angle. Now you have an abundance of information. Now you'll be able to use the law of sines. Off you go. But we should discuss our strategy. Let's formalize our strategy. We're going to set up a hierarchy based on ease of use. How do you spell hierarchy? Hierarchy. I'll need a dictionary. Our strategy for solving oblique triangles is a hierarchy based on the ease of use. First thing that you want to do, as soon as you have two angles, subtract to find the third. That's the easiest one to use. Just have to do subtraction. So first, number one, as soon as you have two angles, subtract to find the third. If I've given you two angles, you're subtraction away from knowing all the angles and having an abundance of information. One level up from this is the law of sines. Use the law of sines if you have a set of opposite information, A and alpha, B and beta, C and gamma. Use the law of sines if you have a set of opposite parts. What I mean is A and alpha. Use the law of sines if you have a set of opposite parts. Side A and angle alpha, that's a set of opposite parts. Side B and angle beta, side C and angle gamma. If this is the first thing you're doing, and the other piece of information is a side, then you have to be careful. So we have to beware the ambiguous case. Ugh, so many rules. It's like this is a math class or something. Oh, that's right. That tracks. We got to beware the ambiguous case. We want to use the law of sines, but there is one situation where we have to be careful. That's the ambiguous case. The ambiguous case happens when we're using the law of sines first. We're looking for our fourth piece of information. Given 3, we're looking for our first new piece of information. If you're using the law of sines first and the other piece of information is a side, that's the ambiguous case. This is called the ambiguous case of the law of sines. The setup is we want to use the law of sines because we have an opposite set, a set of opposite parts. Side A, angle alpha. If we have side A, angle alpha, and angle beta, no problem. Just keep going. Just go ahead and it couldn't be the ambiguous case. But if you have side A, angle alpha, and side B, and this is the first thing you're doing in the triangle, welcome to the ambiguous case. The reason it's called the ambiguous case is that this could lead to 0, 1, 2, or 1 triangle. I know I said 1 twice because it could show up twice, 2 different ways. That's the ambiguous case. The main thing that we have to remember is that this could result in 2 triangles, and we're going to have to find them both. So we just have to make sure that we take that step. And we just have to be aware that we're doing an ambiguous case sign. If we're using the law of sines first And the third given is a side, not an angle. Ultimately, if the third given is an angle, we're not doing the law of sines first. The first thing we did was find the third angle. So really, if you're using the law of sines first, then you got to be careful. I'm going to put in parentheses, and the third given is a side, because it's like you didn't notice that you could just subtract to find another angle. That's just me getting around my own semantics. So those of you watching this on the internet, you can write comments about how my statement is not in. Oh, that's right, I disable comments because I was tired of getting ads for pornography on my friggin' YouTube channel. People just trying to watch math. Oh, click here. No, that's not friggin' on. All right. Third, use the law of cosines otherwise. Sometimes you have to. Sometimes you'll just prefer to use the law of cosines and you'll use it whenever you can. So third, in our strategy, we're going to use the law of cosines if we do not have a set of opposite parts. There's no ambiguous case we need to worry about for the law of cosines. Since we're new at solving oblique triangles, this is the way that we want to start thinking about it. But really our strategy boils down to one rule. Of the three tools that we have, which tool can you use? Use that one first. That's it. Which tool can you use? So this is really only one rule. Oh, let's move this part. Which tool can you use? Use that tool. Technically, we can use the law of cosines in the weirdo cases. If we have two sides at an angle, we can always use the law of cosines, but we're not going to really want to. So it's really, which tool can you use? Do as little work as possible. So here's our strategy for solving oblique triangles. As soon as you have two angles, subtract, find the third angle, use the law of sines if you can. Be careful if it's the first thing that you're doing. And third, use the law of cosines if you do not have a set of opposite parts. The law of sines when you have a set of opposite parts. The law of cosines is when you do not have a set of opposite parts. Remember, as soon as you have 4 pieces of information about a triangle, you necessarily have a set of opposite parts, so you should probably just use the law of sines because it's easier, it's smaller to work with. All right, let's take a break, come back and do a couple of examples of solving oblique triangles.